Have you ever actually stopped to wonder how artificial intelligence thinks? I mean, when we see an AI pull off a complex task, whether it's totally dismantling a grandmaster at chess or just figuring out the absolute fastest route to the grocery store, it honestly feels a little like magic, right? But underneath that illusion of intuition is a highly structured, remarkably logical process. At its absolute core, AI problem solving almost always boils down to one foundational concept: search. Welcome to this explainer, where we're going to break down exactly how an AI agent navigates its world, formulates a master plan, and searches for the perfect sequence of actions to hit its goals.
Okay, let's dive right into this. First, we'll clearly define what a problem-solving agent actually is. Then, we'll unpack what search really means in this context. Figure out how to measure success through search complexity, learn how to formulate a problem, and finally, look at how all of this scales up in real-world AI search.
Starting off with Section 1, the problem-solving agent.
So, what actually is an AI problem-solving agent? It sounds like a buzzword straight out of a sci-fi movie, but in computer science, it's a really specific mechanism. An agent doesn't have to be some physical metallic robot. It's simply an entity that perceives its environment and then takes actions to maximize its chances of success.
To be super precise here, our source material defines a simple problem-solving agent as a function that runs on a very specific continuous loop. Think of it kind of like a highly logical person waking up in a pitch-black room. First, it updates its state. Basically, it figures out exactly where it currently is based on whatever it can perceive. Second, it formulates a goal. Where does it actually want to be? Third, it formulates the problem. What are the physics and rules of this room? Then, and this is the crucial part, it searches for a specific sequence of actions to bridge the gap between where it is right now and its goal. Once it finds that sequence, it just executes it, step by step.
Moving right along to Section 2. What exactly is search?
In the realm of AI, a search algorithm is simply how the agent retrieves information hidden within a data structure, which might be a vast tree or a massive, complex graph. It has to look at a dizzying number of possibilities and decide on its next moves. To really wrap our heads around this, let's contrast two of the most basic ways an agent might dig through data: linear search versus binary search.
Let's start with a linear search algorithm. Imagine you have a list of numbers, and you're hunting for a specific target value, say 39. In a linear search, the agent is incredibly systematic, but man is it slow. It starts at the very beginning and just examines every single element one by one. Is 13 the number? Nope. Is 9? Nope. 21? Still no. It just keeps hopping down the line until it finally hits 39. It's totally foolproof, sure. But imagine if that list had a billion items and your target was at the very end. Our agent would literally be exhausting itself checking hundreds of millions of wrong answers first.
Now contrast that with something much more efficient: the binary search algorithm. For this trick to work, the list must already be ordered from smallest to largest. Instead of checking one by one like a linear search, the agent jumps straight to the dead center of the list. If our target is 35 and that middle number is 25, the agent instantly knows that the entire lower half of the list is completely useless, so it just discards it. It continuously divides the remaining possibilities in half, zeroing in on the target incredibly fast. It's basically the difference between reading a dictionary page by page to find a word versus opening right to the middle and tearing the book in half over and over again until you find what you need.
That brings us to Section 3, measuring success, or search complexity.
To measure how well these searches work, computer scientists use something called Big O notation. Now, please don't let the math terminology intimidate you, because it actually tells a really intuitive story. Think about two things: the input size, how massive our data is, and the number of computations, how much actual elbow grease the agent has to put in. With a linear search, represented as O of n, as the data grows, the workload grows steadily at the exact same rate. It's a steep hill. But with a binary search, which is a logarithmic O of log n, the workload stays incredibly flat. Even as the data gets massively bigger, the amount of extra work the agent has to do barely increases at all. Finding a search with that flat curve, that's basically the holy grail of efficient AI.
So the crucial takeaway here is that we actually have to measure efficiency in two completely different ways. Time complexity is what we just talked about, how long an algorithm takes to run based on the number of steps. But then there's space complexity. This measures the actual physical computer memory the algorithm consumes while it's thinking. For example, in those searches we just discussed, space complexity is very low, often O of 1, because the agent only needs to hold a couple of tiny details in its working memory like the target value or the current high-low range. Ultimately, a successful agent has to balance both time and space.
All right, Section 4, formulating the problem.
Before our agent can start searching, it needs a rulebook. There is basically a universal, 6-step checklist for setting up any AI search problem. You need these 6 things every single time. 1. What are all the possible states the world can be in? 2. What is the initial state, where the agent actually wakes up or starts? 3. What specific actions can the agent take? 4. What is the transition model? Meaning, if I take an action, how exactly does the world change? 5. What is the absolute goal state? And 6. What is the action cost? How much penalty or energy does the agent pay for making a single move? Let's apply this checklist to some scenarios to make it concrete.
Picture one of those classic 8 puzzles. You know, the little plastic grids with sliding numbered tiles and one empty space. Our initial state is the totally scrambled board. The actions available to our agent are super simple. Slide the blank space up, down, left, or right. The transition model is just the physical result of that slide, right? A number swaps places with the blank. The goal state is getting all those numbers into perfect numerical order. And the action cost? Every slide costs exactly 1 move. To solve this, the agent will rapidly search through thousands of possible board combinations to find the exact path that uses the lowest possible cost.
Let's try another quick one. Imagine a robotic vacuum cleaner in a simple 2-square room. The states are combinations of where the vacuum currently is and which of those squares actually have dirt. The initial state might be that the robot is sitting in a dirty left square. Its actions are straightforward: move left, move right, or suck. The transition model dictates that if it uses the suck action, the dirt in that specific square is removed. The goal state? A completely clean room. And just like before, every single movement or suction action costs 1 unit of energy.
But listen, action costs aren't always a simple 1 move equals 1 point. What if we're planning a road trip? Let's say our agent starts in Vancouver and the goal state is to reach Surrey. The states are the different cities on the map. The action is traversing from one city to an adjacent one. The transition model simply updates our location on that map. But here, the action cost shifts dramatically. It's no longer just a flat cost of 1, it's the actual physical distance, or maybe the driving time between the cities. The agent now has to calculate the optimal sequence of connected cities, say Vancouver to Burnaby to Port Moody to Surrey, that results in the lowest cumulative distance.
Which brings us to our final section, real-world AI search.
Out in the real world, the input size isn't some cute 3x3 puzzle board. It is absolutely staggering in scale. Take VLSI computer chip layout, for example. Engineers use AI agents to figure out how to arrange literally millions of microscopic electronic components across multiple 3D layers on a single microchip. The search problem is immense. The agent has to route connections without a single wire crossing or causing signal interference. Or think about automatic assembly sequencing in a massive automotive factory. The agent has to search through millions of permutations to find the exact, optimal chronological order to assemble a car to minimize time and factory floor space. Those 6 basic problem formulation rules we talked about, they still apply completely, but the search space is just incredibly colossal.
Which leads us to a final thought to leave you with today. Every time you pull up GPS to navigate around a traffic jam, every time your smartphone's processor efficiently routes power to save your battery, every time a search engine instantaneously finds that perfect result, there's a highly structured, problem-solving agent silently operating in the background. It's continuously updating its state, formulating its goal, and rapidly searching through millions of possibilities just to serve you. So, how many invisible agents have you already relied on today without even realizing it? Thanks for joining me for this explainer, and keep questioning the incredible hidden logic powering our everyday machines.